Hey,
All right.
Bob. Good to
Hi,
see you.
Jeff. How are you this morning?
I'm good, thanks. I guess we haven't done this since November of 2020 before the election, so things have changed a little bit since then.
Yeah. Yeah, I'm still here waiting for my vaccine.
I think we both are. I changed jobs, and we have a new president, so it's I guess Happy New Year, even though it's the beginning of February.
Happy New Year.
So you and I have known each other a long time. And when I started out in this business in the early 2000s, I was trained on all types of instrumentation, but primarily magnetic flow meters, vortex flow meters, and Coriolis flow meters. Lo and behold, I meet you. We go to the lab at WashU, and you've brainwashed me on Orifice plates and why Orifice plates are great. So we're going to talk about Orifice plates today, Bob, and maybe you could help enlighten us. You're the fixer. You've fixed a lot of this stuff over the years in your experience. I know you've got some good stories, but let's start with the basics. Can you tell us what an Orifice plate is, please?
All right. Well, basically, it's generally it's a machined type of restriction in the pipeline that creates a head or a differential pressure. It has an upstream and a downstream, or a high and low pressure, and the differential is inferred on the basis of the flow rate. And the fundamental equation for that is from Dr. Bernoulli. So the flow rate is generally proportional to the square root of the pressure drop. So that's kind of what it is. It can essentially be a plate. You can also do it in an elbow or a restriction. There's a whole series of different types there's wedge meters and a whole series, but all these are basically head meters that are function of the flow rate. So the square root of the pressure drop.
Is it fair to say that Orifice plates are probably some of the most trusted flow meters over the years?
Yes, it's probably one of the first ones that started, I think. It's of course, Bernoulli's been known for many, many years, and they're still around, and they're easily understood, and I think they're, particularly in the Gulf Coast or the refinery world, petrochemicals, they're one of the most common meters used.
Oh, I've certainly seen, a lot of installed base. There's still a lot of specifications written around them. But I'm sure, like anything else, with a magnetic flow meter, it's only good for conductive liquids. And I'm sure there's issues with the Orifice plate. Can you tell us about any issues or difficulties you may have seen with these types of flow meters?
Well, the big issue is not so much the flow meter itself, it's the sensing lines, particularly if they're steam lines outdoors where you have environmental issues, freezing, and this kind of thing. Back in the old days at the old Monsanto, we had a lot of problems with the sensing lines on Orifice meters for utility service. Just gave us all sorts of problems, particularly in the wintertime. It'd freeze up and that kind of thing. The plate itself can erode or corrode is a problem. And then entrained solids can be a problem. They tend to lie at the bottom of the pipe. And so you have to have your taps in on the side or in the top usually because of that. So there are problems with them, but most of the problems are known. So it's like the Rumsfeld thing, I guess. You have the known knowns. So you can work around these in many cases.
I didn't know you were a Rummy fan, but maybe that's another discussion for another day. But
yeah.
So I heard you say the sensing lines, and a couple things stuck out there to me. Potential leak points and the freeze protection. What are you doing to prevent the lines from freezing on that?
Well, the latest thing now are these electrically traced tubing and that kind of thing. And with those, it really helps out a great deal. It sort of has been, we used to do it with steam, and that was really a problem. The other issue with them as far as flammable services, you have to put them in pipe, and you have to make sure that they're back welded and so forth, because you can't have, you've got to be concerned about leak points and that sort of thing in flammable or hazardous material. So that's one of the other areas. If you just have a water line, you can get away with tubing. But if you're dealing with any chemical, you have to be concerned about the pipe spec that you have to conform to and that sort of thing.
Okay. Yeah, that makes sense for sure. But electric heat trace and things like that, keep the pipes from freezing. So back to what I said at the beginning. So you've told me over the years, differential pressure flow meters, namely Orifice plates, are one of your favorites because of experience in the field fixing things. I've sat through many ISA presentations, vendor presentations about, the benefits of this type of flow meter, a mag meter, a vortex flow meter, a Coriolis flow meter. Well, why are we using Orifice plates still if we have all these other great types of technologies that have been proven in the field?
Well, one thing is the fact that they're well known. The material that basically how to size it and so forth has been established for a number of years. And the other aspect of it is that you can actually, in a pinch, make these things out of pipe fittings and slip blinds and this sort of thing. And I've done that innumerable times where I've just made them out of whatever I had laying around in terms of piping. I just go ahead and get them piped up. And I did that a lot. So the other thing is you do not need to have an orifice flange. You can actually, there are other pipe taps that you can use, vena contracta, radius taps, and 2.5 by 8 diameter. Usually on a small pipe size, that's the one I usually used, was 2.5 by 8. The other aspect is that there were a number of DOS-based programs for sizing these things. And I made use of Spinx. Has got all the calculations for it that you need. There's also a document that was put out in the 60s by Fisher Porter that has a series of graphs and equations on them, this little booklet. And I've actually made use of this a lot. It's like I say, this thing was published in 1963. So I've been using this for well over 50 years.
Is it copyrighted?
Well, yeah, but Fisher, I don't know. I don't know who Fisher Porter is. I do know that I made copies of this. I scanned it and let my students use it.
Okay, maybe we could look at that. We'll take that offline for sure. So we're using Orifice plates because they're trusted. We talked about, you've had some DOS-based programs over the years, and we'll circle back to that, I think. And certainly Spinx is one of the kind of, I guess it's fair to say, gurus in the industry on DP flow and the Fisher Porter book there. But it's trusted. And you mentioned you've made things out of slip lines and other things. But if you took if I had all the resources necessary, let's say I've got a brand new, I decide I want to use an Orifice plate flow meter, and I have all the resources necessary, a brand new installation. I'm not, piecemealing things out in the field. What are the typical textbook components and things that I would use or specify and buy?
Well, in many cases, people will just buy the plate. they'll go to one of the manufacturers that actually has the plate, and the manufacturer will size it. You generally want to have, as to get an idea of what kind of orifice you need. Generally, the beta, which is the inside diameter divided by the pipe diameter, about 6/10 is a reasonable number to use.
0.6.
And you generally will need to get a decent differential, somewhere between about say 75 and a couple hundred inches of water. And you won't take all of that. You'll recover a portion of that unless you do the 2.5 by 8, and that pretty well figures that you're completely recovered on those cases. That's a sort of like a total drop meter. In most of the cases, you actually are measuring the differential pressure at the vena contracta. So generally, you start simple, of course. If you were going to do this, you would, the simplest one is just a concentric bore. There are other bores for various types of application, whether you have solids and this sort of thing. Concentric bore is the one I've used almost all the time. I did use a wedge meter, which was actually made by Taylor for phosphorus and sulfur flow. But that's kind of a specialized application. I've seen them, as I say, the wedge meter for phosphorus and sulfur. So getting on a brand new installation, you generally would get the flanges spec'd out by somebody. And the newer DCS systems now even have all the calculations in an app. You just basically drag a function block in. And I know in the case of Emerson's, they have a gas block, which I actually used for an integral orifice DP experiment. And you would input the pressure and temperature and the composition of the gas. And if you had a pressure and temperature transmitter, you can actually bring those signals in and get the calculation that way. I actually had my students go in and put one together. They had a regulator where they could actually set, it was airflow. Mm-hmm. And then I actually had them lower the pressure. We had a decent gauge, and I had them lower the pressure, and then they would input in the lower pressure into just a right block, and then they could actually see we had a rotometer there. They could check and see that it read pretty doggone close.
Nice.
Worked out fairly well. So, and many of the newer instrument companies still will advertise orifice plates and what they call a multivariable transmitter, which basically is just what I was speaking about. So that's why they're still around, and I think they definitely have a definite purpose and fulfilling a role in the flow meter application or arena.
So we talked about the flange, the plate, the piping, the transmitter, and that you mentioned the DCS, of course. There's multivariable transmitters out there, DP transmitters, and then sometimes you can even, the DCS have the blocks for calculations in it. But did I cover everything there? Did we answer all the stuff?
Yeah, the only other thing I want to make is for very large flows, there's, of course, annubars and pitot tubes that are used, but there's also a technique which was developed and written up back in the 1930s that used an elbow tap. They actually had a pipe tap across an elbow, and because of the velocity profile across the elbow is different. You actually get a differential pressure associated with an elbow.
Nice.
And so I would think for large flows like cooling towers and that sort of thing, I would definitely consider that. It's a simple thing to do. The other main advantage of doing it with a pipe fitting is the fact that if you put an orifice in that line, you would end up having another non-recoverable loss just by the orifice plate. Whereas if you have the elbow, well, that's part of the piping system, and you're not taking any additional head loss, so you're actually saving energy by using the piping itself or the fitting itself to measure the flow rate. So you're being energy conscious, I guess, in doing it that way.
So that's a great point. Is it fair to say maybe a concentric orifice plate, because of the unrecovered pressure loss, might be a little more, how can we say it, takes a little more energy to run than, say, an open bore magnetic flow meter and an elbow tap or a pitot tube like we talked about?
Yeah, well, a pitot tube would have some restriction in the line that's non-recoverable too. So it's just like the same thing would happen with a vortex meter. You have a blunt object in the line, and you have some unrecoverable pressure losses as a result of having that object in the piping.
Okay.
So. And I've put together some spreadsheets that I have on the website, and also a description of how I would recommend putting these things together. If you're using like a radius tap or 2.5 by 8 diameter taps, I highly recommend you use a threadlet fitting rather than just a coupling, because a threadlet gives you more surface area and volume that you can weld onto the pipe. I believe in those things. And of course, if you have flammable service, you're going to have to be concerned that you follow the pipe spec that's associated with it, and you're putting in a small diameter piping, so probably have to be back welded. So that, I guess, is the downside of these things, is they require more labor to install. You have all the fittings and everything else that are required, and so they do take labor to put them in.
I'm a little slow this morning, Bob, but you mentioned the threadlet fitting, and you caught me off guard. Is that threadlet for the pitot tube, or what are we using the threadlet for there?
Well, the threadlet is what you would, the connection that you would make between the pipe and your sensing line.
Okay, got it.
Yeah, so usually Spink just shows a welding, a coupling in place, but I think you're better off with a threadlet because it's a more robust fitting. And it's sort of designed for that, whereas a cup.
Okay. We talked about pressure drop and pressure loss and things like that, and I'm assuming all good instrument manufacturers would be able to help you run these calculations for you in modern day, or what have you seen, or how are we sizing orifice plates applications? Are we going to the manufacturers, or what are we doing?
I got cut out on that, Jeff.
Oh, yeah, no problem. Technical difficulties happen. So we talked about pressure drop and pressure loss. And I'm thinking that any good instrument manufacturer would be able to help make that calculation on any of the flow meters they have, or differential pressure elements such as orifice plates or pitot tubes. But what have you seen in the field? How are we running these calculations to figure out, to make sure we've got our beta of 0.6, and we know what our pressure drop is going to be?
Well, usually I just, as I say, I've used these these calculations here just essentially longhand, and I've done that for years, or I just use the information that's in here in Spinks. I've used some computer programs I have that run in DOS. There's different applications now. You can still run them in DOS with the right program to open up a DOS program. I developed some spreadsheets, and they're on the website there. For liquid flow, I generally start with assuming that I have a beta of about 0.6, and for liquid flow, you start with the beta, and then you just calculate based on the fluid, and you need to know the fluid properties, the density and the viscosity, where you then calculate the Reynolds number. Anytime you're dealing with any dynamic fluid, you need to know your Reynolds number, which is what I told my students many times. That is something you have to know. And you need to know how to calculate it. And I had in my teaching days a lot of times where we met Mr. Reynolds, and we had to show where he's used, and which is in just about any time you have any dynamic fluid, you have to calculate your Reynolds number. So basically, once you've done that, you're sure that you have turbulent flow. In most cases, you do. And then you wouldn't be thinking about an orifice plate generally in laminar flow. You generally have to have turbulent flow. And for the liquid, I say I start with about 0.6 beta, and you need to get something around 100 inches of water and so forth. And you don't need to do any, it's just a straightforward calculation at that point. Where the calculations get difficult is if you are in a gas or a vapor flow, because then you have expansion across the plate that has to be taken care of. And the calculations are a little more difficult, and you need to actually use, if you're doing it in Excel, you need to use a solver, because it has to find a minimum point in the calculations based on the pressure drop and the other calculations that's used. So, as I say, I've written these Excel spreadsheets, and I use those. Or back in the days of Monsanto, I just used some of their, used some DOS programs and put them together that way. I don't even think I ever bought a plate. I think most of the ones I did, I just got a slip blind and told the guys to drill and tap it out and stamp the ID on the plate and drill a small hole on a tab so they knew that it was a plate. And as I say, that was how I did it. I pretty much rolled my own, I guess is the expression that they used to use. I don't think I ever bought a couple of times I might have bought an orifice run that had everything put together in a smaller diameter, but more often than not, for anything bigger than 2 inch, I basically sort of made my own. I used vena contracta taps or radius taps and just put it together myself.
I'm sorry, my inner teenager's coming out. Rolled my own is something I never thought I'd heard Professor Bob Heider, ISA fellow, say in my life. So it was kind of fun to hear. We got Reynolds numbers. I think if enough people watch this, maybe we can have the Heider number or the Heider method. Roll your own, baby. Something like that.
Yeah, well, it's that expression comes from the days when cigarette tobacco was in bags, and you would get.
I'm familiar.
I guess I have to watch my age and also political correctness, but that's. I think it's instead of roll your own, it's DIY is the expression.
Well, you got me there. You're living.
Do it yourself.
There you go.
that's the. But I guess in my time frame, it was called roll your own.
There you go. Well, so maybe we can have the the Heider number, the Heider method, or something like that. That's the slip blinds, and make it on site there, baby. Do your own calculation. I love it. Look, let's close with this if we could, Bob. So if you can, I'll put you on the spot a little bit. We talked about all these different flow meters. Have you walked into a site where maybe you got called in to fix something? You've seen the mag meter isn't working, the vortex meter isn't working, whatever other flow meter isn't working. Have you ever rescued an application or a process with orifice plates or differential pressure flow meters?
Oh, all the time. Many times. I can't count the number of times I went in and had to rip something out that didn't work. And usually not mag meters. I was able to get those to work. We can talk about those at another session. I had a lot of experience with those. Vortex shedding also. But primarily where the problem was, and this was in the early days of vortex meters, a number of them gave us all sorts of problems and they just didn't work. And so I would have to go in and put in a DP cell instead. And I did a number of those. So I can't even keep track of the number of them I did. But basically, that was a number of those that I can remember. But that was many years ago. And I'm sure that now vortex meters are a little bit better designed than they were initially. There's been many cases where I've gone in. As I say, most of the cases that I had to put one in was a vortex meter that didn't work. I can't recall a case where I ever replaced a mag meter with an orifice plate.
Good show. Good. Well, to our friends in the ISA St. Louis section, everything that Bob and I have talked about, we'll make sure the links are here as part of our episode, and we'll make sure they're up on the website or a website where you can download them somewhere. Bob, to be fair, I haven't used DOS in years. I guess I could get to the C prompt or something like that, but we'll look at these programs and maybe they can run on a modern PC. But to your point, the engineers should be able to do this on their own and not have to rely on a vendor. And your spreadsheet, of course, will upload. So that's this. Can you talk about the spreadsheet for just a second, Bob, and how helpful that may be?
Well, I have several there, one of which makes use of an ASME calculation, which is the calculation and actually all the calculations that are done in this Fisher-Porter. And that one is generally, there's some caveat in there, and I have a accompanied text that goes along with the spreadsheet to explain how to use it and some of the background for it. Those are what's called sort of like plant calculations. Even Spink has a plant calculation and a more of a detailed calculation, because in many cases, an orifice meter is actually custodial. It's used for custodial transfers. So those, they have to be very accurate. But then generally for most plant applications, you don't need quite the accuracy as that. So, and I do know back in the petrochemical days of Monsanto that custody transfers were done, and they would arbitrate their readings each month in terms of getting some hydrocarbons from one plant to another. So, as I say, the spreadsheet is there, and the other thing is, as I say, I've done a lot of them just longhand. And there are some of these DOS programs available. One of them that I have is I don't think I should give away, but the others I could give. In some of them I don't even know who wrote them.
It's all about the copyright law, right? Well, Bob, thank you for your time. Anybody who watches this episode, do you want to? Do you mind if they contact you if they have questions outside what's in this presentation?
Oh, sure, go ahead. I'm willing to talk to anybody, particularly being stuck in here, with the pandemic and not being vaccinated and all. So, yeah, just hope for the best here.
Do you want to share your email address?
Yeah, I think the best thing is a Gmail, robert.heider, Heider, 66 @gmail.com. The other one they can get me on is Heider at wustl.edu. That still works. But then I'd have to answer through another email. Usually it's kind of confusing.
Robert.heider66 @gmail.com. Okay. That works. I know I've talked to you there. So, Bob, good to see you again. Hopefully we'll maybe I can work a little harder and a little faster. We can get another episode.
Yeah. Well,
at this
let
pace,
me know what you want to do next. I'll work up something, and we can talk about whatever. The only other thing I got going is WashU's got to get a new chemical engineering lab.
Hey.
And I got another Zoom call this afternoon on that, believe it or not. Everything is Zoom now. We used to sit together, and drink coffee in places. Now we just don't do that, But we'll get through this, I guess. God willing, the creeks don't rise,
That's right. Until then, roll your own. And at this pace, I'll see you again in May, or we'll try and get it earlier, okay?
All righty, sir.
Good to see you, Bob. Thank you.
All righty. Take care. Bye-bye.